morning, physics fans. How we doing on this fine, sunny Wednesday morning? It's a beautiful morning out there. It's supposed to warm up nicely. It's going to be some nice weather, and it's the temperature they keep on going to go. Temperature going to keep on climbing up, which is awesome. This is my favorite time of the year. We're completing the end of the school year. The weather's getting nice outside. I just wish I could share it with you guys because it is a special time of the year, the last couple weeks of school, and we're finalizing and getting things taken care of. And once again, I miss you guys. I wish you were here too. We can enjoy this together, but you know what? It's our normal, and that's okay. We can do it through video here, and we can share our love for each other through the video in this time of the year that we can enjoy. Maybe you can go outside and enjoy some of this weather and mow the yard today too. There we go. Good idea, because it's supposed to rain the next few days and it'll be swampy out there. We're going to continue on with the notes. We have a few more days of notes. Then we'll do a review sheet and a chapter test over chapter 10, and that will be the last that we will do material-wise in this class. We'll finish up the first law and second law of thermodynamics and what happens with the first and second law of thermodynamics. And once again, there's not a lot of mathematical problems that go through with thermodynamics. As you would advance on in the world of thermodynamics, you get into turbines and you get into all those types of things. Yes, there's problems to do, but at our level, we just introduce the idea of thermodynamics and what the processes are with respect to thermodynamics, and then we go forward. Energy of a system is conserved if the mechanical energy is converted into thermal energy is considered. Okay, if your mechanical energy is converted into thermal energy, the friction, you have potential energy and you have kinetic energy we talked about, but with the thermal energy is the friction that is there, the heat that maybe gets expanded out of that. We'll have conservation when we start talking about that thermal energy. The thermal energy, once again, is the heat. Once again, as we talk about the friction allows us not to be as efficient, not the mechanical, the energy that's put into a system and the work that's being put into the system doesn't always come out of the system because we lose a lot to friction. But the thermal energy is Q, work is W, once again. You have initial and final internal energy, which is U, I, and UF. This is your internal energy that you have. The change in internal energy is delta U, and delta U is U final minus U initial, your internal energy, final and initial. Thermal energy added to a system in the form of heat. Okay, if we have a system and we add heat into the system, that means we're going to have a positive heat, or our Q will be greater than 0. We're taking a system, we're just adding heat into the system. We are warming it up. Your household, the furnace kicks on. The heat gets added into the system. Okay, thermal energy is removed from a system in the form of heat. Then what we have is we have Q is less than 0. Once again, you have the heat pumps, your air conditioners, their central air, okay, which you may have to kick on next week. Oh yeah, okay. It takes heat out of a system. Well, that's a minus Q then. And your house is basically your system. It's an isolated system. But we don't have a perfect system within your house because you have insulation, but you lose some heat from the insulation, or your windows may not be good. You can lose heat or you gain heat in regards to some inefficiencies with your house. If no heat is transferred, you have no heat, then your Q is equal to 0. And remember, when we're talking about this, we have work is equal to pressure times our delta V, because we'll use this down here. If work is done by a system, that means you have expansion of a gas. Okay, if work is done by a system and you expand the gas, this means your work is going to be greater than 0, which means you have a positive work, which means if you have a positive work, we have a positive change in volume. as you heat up gas, the volume will also increase. Okay, as you heat up the gas, the volume will also increase. Okay, they're inversely or they're directly proportional. Addition of heat, addition of volume. Take away heat, take away volume. Okay, in a gas. Okay, so work done by a system, which is the expansion of a gas. You have a positive change in volume and also positive change in work. Work on a system, which is a compression of gas. Okay, you have less work, or your work is less than zero, negative work, or your delta V is going to decrease. Once again, they are directly proportional without the work, and the volume, change of volume, are directly proportional. If no work is done, then your work is equal to zero. Your delta V is equal to zero. Okay, and this is all things that we've talked about a little bit. The first law of thermodynamics. The change in the system's internal energy is equal to the energy transferred to or from a system as heat minus the energy transferred to or from a system as work. The change in internal energy, delta U, is equal to the energy transferred to and from a system as heat minus the energy transferred to and from the system as work. And once again, we have this change in internal energy also as U final minus U initial. Your internal energy final minus your internal energy initial. Let's see here. Energy conservation requires that total change in internal energy equals the net transfer of energy as both heat and work, which means your delta U is equal to Q minus W. The amount of heat minus the work. The heat added into and the work that is done. We look at a problem here. A system does 5 joules of work. The system does 5 joules of work, and 7 joules of heat is added into the system. Calculate your delta U. Well, what we have here is when the system does work. When the work is done by a system, your work is positive. Okay, so we have a positive 5 there. When heat is added into a system, that is a positive 7. Okay, so your work is positive 5 and your joules is positive 7, or your heat is positive 7. And these are all joules. So your change in internal energy is 7 minus 5, which is a positive 2 joules. That's going to be your change in internal energy. And if you think about this, the system is doing 5 joules of work, whatever the system is. But you're adding 7 joules of heat into the system that is creating this 5 joules of work. Okay, so what you're doing is you're taking the heat energy and transferring that into mechanical energy, whatever work that is. Okay, you have 7 joules of heat going in, 5 joules of heat are used to do your work. That means you have 2 left over. Heat added to a system. Once again, this is going to be a positive Q, which we just had up here. Work done by a system is positive work. Heat lost by a system is negative heat. And negative work. Work done by a system is negative work. Or work done on a system is negative work. So if you're doing work on the system, that's going to be a negative work then. If no work done on or by a system, that means our work is equal to 0. And if no heat is lost or gained into a system, we have Q is equal to 0. And once again, if I'm going too fast, hit your pause button. Hit your pause button. I promise I won't continue to talk. Once again, a lot of theory behind heat and work in a system. Okay, not a lot of mechanical or mathematical work being done here. Well, let's take a look at the isovolumic and isothermic and oh gosh, I always get a tongue twister on this. Adiabatic system. We'll take a look at the systems. If you have, and remember our delta U is equal to Q minus W. If you have an isovolumic system, that means delta V is going to equal 0. The volume is not changing here. Our change in volume is 0. So if I look at pressure times my change in volume, which is equal to work, our amount of work is equal to 0. In an isovolumic system, the amount of work is equal to 0 because we have no delta P or delta V. Well, what happens to our first law then of thermo? What does this reduce down to? Well, our delta U will then just equal Q, because this value of work is going to 0 because I have no work in an isovolumic system. Why? Because I have no delta V. I have not changed my volume at all. So if I haven't changed my volume at all, I haven't had work. Okay? So I have my delta U is just a matter of the change of internal energy. It's just the amount of heat that's being either added or taking away from the system. Okay, we can add heat into a system or we can take heat away from the system. All heat added to the system, that means Q is greater than 0. It raises your internal energy because you've added heat into the system. And if you've taken heat away from the system, that means you'd have a negative Q. You would reduce your internal energy. What if we had an isothermic system? No change in temperature or internal energy. What happens to our first law of thermo? What's it reduced to? Well, our delta U is going to equal 0. Okay, so I have no change in internal energy in an isothermic system. So I have no change in temperature or internal energy. What does the first law reduce to? The amount of heat that gets put into a system gets taken out as work, which would be a perfect 100% efficient system. Probably not going to happen. But the amount of work that's been done, the amount of heat that gets added in, since I'm not changing any internal, I'm adding heat into a system, but I'm not changing any of the internal energy, because heat would naturally expand, look to try to expand and increase the average kinetic energy. But what's happening in this situation is I'm not changing any of the internal energy, so all the heat that gets added in gets taken out as work. Once again, that would be a 100% efficient system that you have there, which is probably not going to happen. Not all heat added into a system gets taken out as work. Okay, you'll have some friction there and you'll have some loss of heat there at that point. So what happens in a isothermic system is the kinetic energy. Remember, when we add heat into a system, that increases potential energy or increases your kinetic energy, and objects want to move faster and faster, which should expand and change our volume. But in an isothermic system, we are not changing the temperature at all. So if we're not changing the temperature at all the work, all the heat that's getting added into our system just gets converted into the work. What happens when work gets added into a system? It gets removed as heat. And what happens when heat gets added into the system? It gets removed as work. Once again, that's what happens in an isothermic system. everything going in comes out as the other. Once again, that's a perfectly efficient machine, and we would have a tough time creating that. A diabatic system, I have a tough time with that. No energy is transferred as heat. That means our Q is equal to 0. Remember, that is our fast filling up a helium balloon, okay? And everything is ice insulated. So if everything is insulated, everything goes from this to this, and you have no change in heat. What happens to the first law once it gets reduced down to? Our delta U comes down to negative Q, or negative work. So work done by a system. Work done by a system, that means our work is going to be greater than 0, will lower the internal energy. What does work done on a system do? That means our work is going to be less than 0. That's going to increase our internal energy. Isolated systems, no energy is transferred as heat and no work is done by a system. That means our Q and work is 0. It's isolated. And what happens to the first law of thermo? Our delta U turns into 0. Our delta U, since our Q and W our change in U is equal to Q minus W. Well, both of these go to 0. So our delta U is going to equal 0, which is UF minus U initial, which means our internal energy final, maybe, is equal to our internal energy initial. So our initial internal energy is equal to our final internal energy. So these two will be equal to each other. And this is the first law of thermodynamics. And once again, just a lot of theory behind what is occurring in these types of systems that we have. But they're used, these theories, even though they're not perfect, these are used, or people try to gain 100% efficiency in our systems. They try to continue to make our furnaces more efficient, our refrigerators more efficient. They try to make all of our mechanical things more efficient. All the machines that we use, because we want to make them efficient, which means it's going to save us some money as we go along. But they use these ideas that they have here and trying to maintain a perfect machine. Okay, a perfect machine's not going to occur, but we can try to achieve it by using these processes and the thermodynamic processes to make them more and more efficient. Okay, once again, a lot of theory here, not much in regards to numbers. Okay, so mathematically, you're not going to have too much to do in this section or in this chapter. I will post some questions, and once again, please do try to answer the questions. I use that as a class involvement in regards to doing an evaluation with you at the end. So please go back and look at the notes. It's sort of like my exit tickets to be able to check to make sure that you are going through the material. If you have any questions, feel free to ask. Other than that, I have nothing else for you. Enjoy some of the sunny, warm weather today. Make sure you take care of things that you need to take care of. If you're missing assignments, please take care of them because we are quickly coming to an end here, folks. Quickly coming to an end. Yay! And once again, I wish I could enjoy it with you here in the classroom, but it's okay. We'll be fine. But if you have any questions or any problems, please do contact me. Other than that, adios. I'm out of here. Folks, have a great day. Enjoy the weather.